Monday hours to Tuesday morning. So 7:30 a.m. to 8:30 a.m. on Tuesday morning, she'll offer her hours instead of Monday. Okay? So if you wanna take advantage of that, that'll be this week only. And then she goes back to her regular hours. A quick announcement on the homework problem. MagCore, whatever problem that is, one that talks about the magnesium production for magnesium chloride. One, at the end of the problem, it says, okay, you've got a salt solution. Some of it is magnesium chloride, and some of it is other chlorides, things like potassium chloride, sodium chloride, and lithium chloride. I forgot to mention that for you to solve this problem, you have to assume that this other chloride solution is equimolar amounts of lithium chloride, sodium chloride, potassium chloride. What do I mean by equimolar? That there's the same number of moles of each of those compounds. You need that to figure out the molecular weight. Okay? So those two things, and you should be able to do the homework. If some people have been using the discussion section on Canvas, I hope that you found that already for homework. It's a great way to get quick responses. Me and Emily have been really fast about responding to things. We don't want you to sit and not know what to do on a problem. Okay, that said, we're going to finish chapter 16 today, and we left off last time, and we'd said that, great, we can use these standard reduction potential tables, and we can say the lower one on the table has the more negative voltage. And since voltages are just opposite of free energies, where a positive voltage is spontaneous, then the one that has the more positive voltage is going to happen as it's written. And as it's written, it's a reduction reaction. So the one that becomes oxidized is going to be the one that's lower on this table. All right? So we gave some examples. We said if you had iron and zinc put together, which one's going to be oxidized, meaning which one's going to turn into ions and corrode away. And we decided it's zinc because it's more negative. So we switched it, we made it an oxidation reaction, which changed its voltage to positive from negative before. And then the overall reaction for this, you just add these two voltages together. Okay? So that's a start. It gets a little more complicated, right? So that only works for standard temperature and pressure, and if you had equal concentrations of the ions in solution. But those things don't have to be the same. They can be different. Just like in a chemical reaction, you could have a gas being produced on each side, and you could say, okay, at standard temperature and pressure and equal partial pressures on either side, what will it be? Right? But you can have different partial pressures. So we can do the same thing for batteries. If concentration changes, that can also change what the voltage will be. In fact, it can even reverse a reaction that looks like it'll be spontaneous. It can switch it. The very first homework question, I think, that you do from the book has an example of that, where you think it's going to be one thing, but when you plug in the concentrations, I think it actually switches it. Okay, so the first equation to note in relating free energy to voltages, so electrochemistry, how do you relate electrochemistry to free energy? This right here, the change in free energy for a reaction, delta G naught, equals negative NF delta V naught. What are some of these variables? N is the number of electrons transferred. So in the case above, if we go back up just a second to this case, what was the number of electrons transferred? 2. When we added these together, the 2 electrons had to cancel on both sides of the equation. What if we'd done an example, and we'll do it in just a second, what if instead of zinc 2 plus it had been something 1 plus, sodium plus, potassium plus? What do we need to do to this? You're going to have to multiply that one by 2 to get 2 electrons. Here's the catch. You do not multiply the voltage. That's the catch. That's where a lot of people make a mistake. In free energy, we multiply the free energy. You do not multiply the voltage here. I don't have a great way to explain that without you having taken physical chemistry. It has to do with, maybe the right way to think of it is if you need more electrons, you're going to get more current, but not necessarily at the same voltage, not necessarily more voltage, right? So you do not multiply that. Our chemists are smirking at me because they have good answers for it. Dennis.
If you think of it like a waterfall, so like if you increase the amount of water that's coming off of the waterfall, the cliff, like it's not going to change the potential as long as that cliff's at the same height.
The potential being the height of the cliff.
Right.
So water, as it falls down the cliff, that's its potential energy.
Right, but like if you have a higher cliff, then the potential energy of the water will change.
So in this case, increasing more electrons is like having more river flow off it. It increases the current without necessarily increasing the voltage. That's kind of the best way, I think, to think of this. Free energy, you definitely multiply the free energy. But for voltages, they stay the same. Okay? Hand over here. Alex, is it?
Yeah. Just to clarify, so your voltage is going to be the same for a given reaction, no matter how much of the reaction is occurring.
Exactly. Well, just to make sure, no matter how many electrons are necessary for the complete redox reaction, no matter how many electrons you have to use for the complete redox reaction, you're gonna get the same potential or voltage. Okay. Now voltage can change, but that's gonna be based off of concentration and temperature and things. Okay. So let's talk about that right now. Using this expression here, how free energy relates to electrochemistry, we know that N is gonna be the number of electrons. F is gonna be Faraday's constant. Faraday's constant is 96,500 coulombs per mole. It's in the book. So it's on page 667 if you have this edition, the third edition. It talks about this. Okay? So let's do an example. Let's do one where, let's see. So before we had this, we had delta Rg equals delta R, so the change in free energy for a reaction equals the theoretical component, right, based off of standard values, plus RT, natural log of Q. So this is going to be completely analogous to it. All we have to do is plug in this relation everywhere that we see a delta G, and we get this relationship, right? It's completely analogous, right? It still has a theory component, and it still has an experimental component. We just had to modify it by basically N and F, right? And you'll find that if you plug in the gas constant temperature, N and F, that will come out in units of volts, and it needs to, since you're solving for something in volts, okay? So what have we done over here? What's this thing? Well, now instead of having Q, I've replaced it by Q equals the concentration of the oxidized species. Square brackets means concentration. Square brackets means moles per liter. Right, concentration. And this is over the concentration of the reduced species. So there's one catch, is I've left off the exponents because the exponents will depend on the chemical reaction. Right? That's going to depend on the actual reaction. So let's do an example. That's the easiest way I think to teach this. Let's do an example of a reaction where N equals 1 for one of the compounds, meaning there's one electron being transferred, and for the other one, it's going to be N equals 2. So let's do it for, what do I have right here? Okay, for silver, Ag plus is going to pick up an electron to form Ag, silver, right? And that, the voltage, the reduction potential associated with that is 0.8 volts. Okay? Now you have another one, cadmium 2 plus. Cadmium 2 plus can pick up 2 electrons to form cadmium metal, and the voltage associated with that is going to be negative 0.403 volts. So the one that's more negative is the one that won't be spontaneous, therefore we have to switch it. That's cadmium, so we switch it. Get rid of that, and let's rewrite it as cadmium metal dissolving to form cadmium ions, 2 plus 2 electrons. Now if we add these two reactions together, the electrons don't cancel out, right? We have 1 as a reactant and 2 as a product. So we need to multiply the silver one by 2. So let's do that. We're going to take this and we're going to do 2 times that whole thing. And then when we add them together, we have 2 silver 1 plus ions plus 2 electrons plus cadmium metal is going to yield cadmium 2 plus 2 electrons plus 2 silvers. What did the voltage do? We don't multiply this by 2. Do not multiply by 2. Okay? So we just add these two together. The voltage is now going to be equal to a positive 0.403. So when you add those together, it's going to be 1.203, right? So the change in V, we'll call that change in V naught, equals 1.203 volts. Okay? Any questions on that much? So then the next step to finish writing this, what will be the total voltage, right? Because we've only solved for delta V naught so far. What's the actual voltage this battery will give you will depend on the concentrations. What's your name?
Sam.
Sam.
My question was, so let's say the voltages are both negative.
Okay.
You switch the one that's the least negative.
You switch one that's more negative because in free energy, the more negative value is the favorable one.
Right, okay.
But for voltage, the more positive one is the spontaneous one. So the one that's more negative gets flipped. Sorry that they did that. I don't love it either. Okay, so we write our expression. Let me switch to one more color. We're going to say that delta V equals delta V naught, which is just this guy. right? And then it's going to be minus RT over NF natural log of what? What should be our reaction quotient? What should this be? It's going to be products over reactants, just like always. Anything that's a solid, like silver metal, we can just call it has an activity of 1, so we can just leave it off. So silver, the electrons cancel out, so we don't care about those. So we've really only got 4 things. Silver metal, which we're going to ignore. Cadmium metal, we're going to ignore. Cadmium ions, that's a product, so let's write cadmium ions over here. We need to know the concentration of that. And then it's going to be over the products, which is silver ions. What do I need to do now? What's missing? What's that?
The power, you have to raise.
Yeah, we said that these exponents, they depend, in partial pressures, you raised the exponent was the coefficient in front of the number. It's the exact same with concentrations. Since we have 2 silver ions, we need to make this squared. There was only 1 cadmium ion in this reaction, so it's not squared. Okay?
Question.
Yeah.
Why do we not care about cadmium metal and?
Technically we could. Up here in our Q expression, we could also include, like, we could just as easily include the metal that is oxidized, or I guess it would not be that, it would be the metal that's reduced and the metal that's oxidized, but because they're solids, they have an activity of 1, so we can just not write them, right? Now, in real world, when you guys take thermal, you'll find out that nothing has an activity of exactly 1. It's always a little bit off, but in this class, we're going to assume that solids and liquids, that you don't have to include them in the quotient, reaction quotient, because their activity is just 1. And that's an assumption. That's not real world. It's kind of close. Okay? Good enough for this class, right? We're complex enough with this topic. Okay? Any questions on this? Ashley? No. Sorry.
What if the metals are alloys?
What if the metals are alloys? Yeah, it would change. Right? It would absolutely change. So that's when you have to look at Galvanic Series. So let's do that. Galvanic Series take into account real materials, not necessarily just pure elements. So Galvanic Series they're very, very similar to what we just saw, but they actually have real materials. So they're listed in terms of reduction potential or oxidation potential, but they're actual real materials. So that you know if you put them together, which one's going to corrode. Sometimes they'll even list a voltage. Sometimes you get ranges, right? Cadmium, it's given a range. Or maybe it's aluminum. Aluminum alloys have a range. We did an interesting, I don't know if anybody saw this, but I made an announcement about aluminum that I thought was kind of interesting. Where's aluminum on here? Aluminum's clear down here at the bottom, meaning it should be corroded, it should be oxidized very easily, meaning it would be a really good sacrificial anode. But in class I said I wasn't sure if it was actually used because aluminum forms aluminum oxide super easily. Anywhere you see aluminum. I don't know if it's aluminum, but if it is, this has aluminum oxide on it. You can't tell. It looks like aluminum because it's a very thin layer, and that thin layer prevents further corrosion because it's insulating. It's electrically insulating. So I was like, that's probably not used, and Nathan, wherever he is, came up and told me, hey, it actually is used. It's the #1 most commonly used one. So I looked into it, and in fact, for a long time they couldn't use aluminum until, this is an interesting article where they talk about it, in the middle of like 1950s or so, they found an alloy by adding a little bit of bismuth, I think it was, and something else they talk about it. By adding a little bit of zinc and indium, that's what it was. They can make it so it doesn't form that oxide and it oxidizes like crazy. So it's a cheap, easy way to get something that oxidizes preferentially. So if you want to read more about it, I think it's a good article. I think you'll learn a lot. Okay, so let's keep going. Let's do a few examples now. So first let's do a clicker. Let me fire up the clicker thing. So the receiver number is the same, 41, but the session ID is different. It changes every time I do it. So the session ID is 464428. And when I click start, it'll still be there, so don't worry. So I'm going to hit start to the polling. It'll pull up in just a second. Okay, so there's the channel ID and the session ID. So everybody get logged on. And while you're getting logged on, let me ask this first question. The question for today that we're going to start out with, if we remove metal from an aqueous environment, will this guarantee the stop of corrosion? By the way, if you're having a hard time with these clicker questions, these should be simple if you've done the reading. If you do the reading ahead of class, you should be getting all your points for these, for sure. So today's question is, first one, if you take it out of the aqueous environment where you have, your concentrations of the salts, zinc 2+ for the zinc metal, cadmium 2+ for the cadmium metal. If you take it out of that, can we guarantee the stop of corrosion? Yes or no? Okay, another 30 seconds. Okay, get your answers in. Yes or no? Can it corrode? Final answers. Okay. People think what? People think no, that it cannot corrode. It can. I'm surprised.
Wait, no.
Did I say that wrong? Oh, okay, good. I was like, for real? Okay, good. Almost everybody thinks it can still corrode, because almost every one of us has seen something that's corroded, even though it's not in water, right? So what can happen? Oxidation. Somebody said it. Oxidation. So which means there's something in air itself which can be involved in what? A redox reaction. Corrosion means redox reaction. So something in air itself can be reduced or oxidized, right? In fact, since your metal's getting corroded, oxygen's probably getting reduced and your metal's getting oxidized, right? So oxide formation is a real problem. You can see it all around us, right? If you take silver, right? If you have a grandma, whoever made you like polish like the silver, you're removing tarnish. Tarnish, I think, is actually on silver, probably a sulfide, not oxide. But still, things in air can react with your sample, even though this thing never got dunked in water and left there. The basic equation is you start with metal, you pick up half of an O2, and you form a metal oxide. Obviously, this is going to depend on the valence of your metal. Aluminum, we know how many valence electrons does aluminum have? It has 3, right? If you go to our periodic table, favorite periodic table over here, it's got 1, 2, 3. It can probably lose its 2p1 in both of its, sorry, it's 3p1 in both of its 3 s's. So it can be plus 3. So if it's plus 3, what will be the chemical formula that alumina forms? It's going to be, yep, Al2O3, right? So whatever your oxidation state of your metal is, you can guess what the formula would be. If it's sodium, what will sodium form? Well, it's sodium plus. It's going to be Na2O, right? Okay? So what would these oxidation and reduction reactions be? Generically speaking, the oxidation reaction is going to be metal going to metal 2 plus 2 electrons, right? It's still losing electrons, right? That's oxidation. If you lose electrons, oxidation. Therefore, it must be the oxygen going from elemental oxygen. It must be picking up 2 electrons, right, to form oxygen 2 minus ions. Okay? Realistically, how does this work? You've got a metal surface, like aluminum, right? Aluminum metal. And oxygen from air comes over to it, and it's going to form what's called a scale, right? A metal oxide scale. This scale, we'll write it just as MO, right? Metal oxide. That can be formed one of 2 ways. It can either be formed, or rather, not formed. Form, it's going to form just by the first reaction. It can grow one of 2 ways. It can grow by either oxygen moving through, oxygen 2 minus moving through the scale, or your metal ions diffusing out to the surface, right? One of those things has to happen, okay? Now the question then is, and electrons would go this way. Electrons would have to go that way. So you cannot get scale growth if this oxide layer, this metal oxide layer, can't conduct electrons. You have to be able to transfer electrons. So that's why alumina, even though it's incredibly low on that reduction potential, meaning it wants to be oxidized very badly, it does not, it doesn't look like it's oxidized, right? If we find anything that's aluminum, maybe the legs of that chair, I don't know if they're aluminum or not, it won't look like a metal oxide because it's a very, very, very thin layer of this metal oxide, but it's electrically insulating, so electrons can't move through it. So once it forms a layer, it's known as a passivating layer, and it prevents further corrosion, right? Which is why aluminum is such a great thing to make bikes and boats and all sorts of things out of, because it doesn't corrode. In reality, the only reason it doesn't corrode is because it corrodes really well the first time and it forms a protective layer that then corrosion can't build on. There are questions on this? Sam?
Is it easy to like scratch that layer off?
I don't know if I could answer that like relatively like easy versus hard. You can remove it. If you take steel wool to alumina and you keep on doing it, aluminum metal, which has that alumina. If you ever hear me say like alumina, that's just aluminum oxide. That's just what people say. Like calcia is calcium oxide. But you could remove it over and over and over. And if you do that, eventually you will like abrade. There will be abrasion that will remove your material enough to the point where it can corrode. But generally speaking, it's pretty long-lasting, pretty great protective layer that it forms. Alex?
So is that just because the aluminum metal is a pretty solid metallic bond?
Like, why does it form that strong layer?
Yeah, well,
That's
I'm assuming that it's just like your metal ions are not moving through that scale surface.
That's a perfect question. Why is aluminum so good at forming an aluminum oxide layer that's so tough? That's exactly the next thing we're talking about. It's known as the pilling-bedworth ratio, named after two people who figured this out. They basically said, all right, how do we know if this is going to work? Well, imagine that like these people on this row in this middle section are all atoms, right? So if I'm going to form a metal oxide at the surface of this, if this is the surface right here, how's that going to work if the metal oxide I have is somebody wearing one of those sumo suits, right? So if I'm wearing a sumo suit, I'm this big, right? So one Rachel now got turned into one Sumo Taylor, right? Which means well, Ryan got turned into Sumo Taylor right here, but I don't fit, right? So it's going to be a mismatch, right? And if we try and like match us up, eventually you can't make these fit. There's too much strain. Strain has an energy component with it, and so it's going to spall off. Have you ever heard that word spall? It's when you form an oxide, but it's not adhering very well below it simply because of size. That's really what it is. It's just you can't accommodate the same number. And if I'm too small, the same problem happens, right? If somebody's really skinny, you're trying to match them up with the same number of rows, you're going to get strain if it's too small. So if it's too small or too big, you get a layer that's going to fall off easily. So as soon as this sumo layer decides to fall off, it chips off, now you've got exposed metal again, you can turn those into oxides and the process repeats itself. So what you want for a passivating layer is you want the volume occupied by the metal to match the volume occupied by the metal oxide. In alumina, it does really well. Other things it doesn't, and it constantly chips off. That's what happens with sodium, with potassium, these things where they just continually oxidize in air. Even though you don't even touch it, it's just oxidizing and falling and crumbling before your very eyes. It's because it has a terrible pilling-bedworth ratio. So how does it work? Pilling-bedworth says the volume of the oxide over the volume of the metal. If that equals 1, then they're the same volume, and it will fit, right? And you don't get spalling, right? Well, how do you know what the volume is? The volume is going to be related to the density and the molecular weight, right? So by the time you take, if you remember that density equals mass over volume, and we're solving for volume, then I guess we want volume equals mass over density. So if you take mass over density, but divide it by mass over density, that's where you get this weird relationship here. Technically, you need to account for the number of metal atoms in the metal oxide. So if you've got V2O5, N equals 2, because there's 2 metals per oxide. Okay? So if the pilling-bedworth ratio is less than 1, as in potassium forming potassium oxide, what do we have? I didn't write it down. If it's equal, we know that's easy. If it's equal, it's going to be protected, like alumina. If it's less than 1, what does that tell us? If this ratio is less than 1, what does that coating look like? You take the volume of the oxide divided by the volume of the metal. It's less than 1. What does it look like? Looks like Swiss cheese, right? Like it's got holes in it. There's too little oxide. Therefore, if it's Swiss cheese, then oxygen from air can go right to the metal underneath it and keep on oxidizing. Okay? So that's bad. Swiss cheese.
So does that mean that the metal atom is too big or too small to accommodate the oxygen?
It means that, well, it's not, it's the volume. It's the volume, not just the metal of the metal ion, it's the volume of the oxide itself. It means that the volume of the oxide is smaller proportionally. When you compare number of metal atoms in both of them, it's too small. It's too small. If it's greater than 1, what would happen? Yeah, it's going to be, it'll start to fall off. And if it's really bigger than 1, like between 2 and 3, then it'll definitely fall off. So actually, if it's between 1 and 2, it's kind of the sweet spot where it'll probably stay on. We should look up what it is for alumina. We could do that, but it would be between 1 and 2, I'm pretty sure, or close to it, right? So this will generally be like okay, and this will be bad, spalling off, okay? So this is, again, this is just an approximation. These folks who came up with this, it's just a general rule. I'm sure there's things that break this rule, but it's a general one that's a decent one to follow. And it's going to tell you whether or not things oxidize continually or whether they passivate. All right, weight gain, there's the very last part of chapter 16. I had you read sections 16.1, 16.2, and then jump all the way to 16.10. 16.10 is talking about oxidation, and they talk about weight gain due to oxidation, right? If this phone were a metal, right, and it's going to form an oxide, then all those metal ions are still here that I started with, and I'm adding oxygen in addition to it. So the weight would actually gain of this thing as the metal oxide were to continue to form. So if you plot weight gain against time, if you could measure this, you'll find that there's different time dependence. There's parabolic, there is linear, and there's logarithmic. And basically the rate at which it grows tells you something about the mechanism of oxide growth. If it's parabolic, then it's probably a non-porous oxide that adheres to the surface. Therefore, if it adheres to the surface, ions have to just diffuse through this layer. And we said that's really slow for things like alumina. Okay? So that's going to be parabolic. If it's linear, then spallation occurs and it must be very porous, meaning the longer you leave it there, the oxide just keeps growing at the same rate. It's linear, right? So therefore, the oxide's not doing much to stop it or slow it down. And if it's logarithmic, that's sometimes observed for thin film growth. Oh, this one's for Al2O3 actually. Okay. Okay, there's more reading on thermodynamics. I think we've given you a lot of resources. We've got 20 minutes left. Let's do a couple examples. So this next example we're going to do, get this out of the way. It's the same thing on both screens you're seeing. If you take this reaction, 2 SO2, right, 2 moles of the SO2 gas, and you combine it with oxygen gas, you can create 2 moles of SO3 gas, right? If the equilibrium constant K is 10, what do we mean by equilibrium constant? Well, we know that the reaction quotient is Q, and Q equals K at equilibrium. So it's just another terminology that is used. If I'm talking about K, that means that delta, so at equilibrium, it means that delta Rg equals 0. That's all that means. Q is just the same as K. You calculate it the same way, but it's a special value of Q when you're at equilibrium, okay? So if the equilibrium constant is 10, okay, so I've given you that, and I say the temperature, it's 960 K, calculate delta Rg, excuse me, that's wrong, delta Rg, and indicate the direction of spontaneous reaction if we have these things initially. Okay, so we'll work through this together, so I don't want people to stress over the points on it, but turn to your neighbor and tell them how you think you would start this problem. Okay, who wants to tell us how you think you'd get started? Somebody who's never answered in class before. Anybody? Anybody feeling brave? Come on, Jake, you do it all the time. Jackson, Jake? Jake. Somebody other than Jake. Nobody? Like everyone's looking down. Okay, let's do, in the black shirt who just looked down at me. I forgot your name. Yeah, you. Patrick, how would you start on this problem?
I have no idea.
Okay, that's all right. That's why we're doing examples in class. So, anybody think they have an idea? Should we call on Jake? Or remind me your name.
Dana.
Dana, how would you start this?
You could calculate Q with the values given and compare it to the K.
That's a great way to start. Let's take the values given, calculate Q, and see how that relates to K. That's a perfect place to start. Let's do that. Let's say what Q is. So Q is going to be equal products over reactants. So it's going to be the partial pressure of SO3 raised squared, because there's two number coefficient right there. And then we've got a partial pressure of O2, that's just to the 1, multiplied by partial pressure of SO2, that's going to be squared. right? And we have values for these things. So it's going to be 1 e to the negative 4. They're in ATM, so we're fine to use them. 0.2. Is something wrong? There's something wrong? We're good? We're good, right? Okay, we're good. Oh gosh, no, we're not good. Why did they do that? Okay, there it is. This thing is squared. This thing is 1 e to the negative 3 squared. Okay? Somebody punch that in. Tell me what you get. What does somebody say 0.05? That's what I got. Yeah, question?
Yes, the exponents are determined by the coefficients of the number of moles of whatever.
Correct, yeah. So we found out that Q equals 0.05, which does not equal K, which means with those things initially, right, what do we initially have? We are not at equilibrium, right? We're not at equilibrium. Yeah, we're not at equilibrium, okay? So which way will the reaction go? Calculate delta RG. Okay, if equilibrium constant K is 10, so we skipped a step. What do we need to do next? We skipped a step. I'm going to pick on our chemists in a minute because I know they know how to do this. Find delta G what? Delta G0. Why do we have to find delta G0? Why was it a problem that we skipped that step?
Because you need to find the free radical component first.
Yeah, total change in free energy of a reaction tells us whether it's spontaneous forward or backwards, but this depends on delta RG naught plus RT natural log of Q, right? So we basically, if we know Q, we could solve for this part of it, but we can't know this until we know that part too, right? But I've given you enough information by telling you what K is to solve for delta G naught, and let's do it together. Okay? So at equilibrium, we know that delta RG equals 0, and that still equals delta RG naught plus RT natural log. We're going to write K instead of Q because this is now defined at equilibrium, okay? So I've told you what K is. I've said it's 10, right? I've told you the temperature, so we know everything to solve that, right? This is 0, so you can solve for this one, right? So let's do that together. So turn to a neighbor and try and figure that one out. Let's solve that. The values are... Can't quite fit them both. Okay, anybody else getting that same value? Yes? Anybody not getting that? Everybody lost? Jake's lost.
Why is it negative?
Why is it negative? Okay, because this equals 0 over here, so delta RG naught plus RT equals that. So I just moved the RT over the other side and says that delta G naught must then equal to negative RT. Good? Okay, so everybody got to this point? Everybody following me? So now that we've got that, what do? Turn to your neighbor and tell him what you do next. All right, Jimmy, what do we do next? You gotta help me out here. Let's say that big fold, right? But we're going to keep it back to 4. And how do you know whether it's going to be a 4 or backwards? Positive, then we're actually back. Okay, good. Good. Yeah, same thing. Okay, so how do we do this? What's the next step? Can I pick on in the light blue shirt? I forgot your name. No, that's okay. Who is it? Dane? There with the glasses, not looking at me? Probably not. Simone, let's go with Simone. I'm bad with names today.
So since we know the delta RG naught at 960K.
You know delta RG naught at 960K.
You can then plug that into the delta RG naught plus RT ln Q.
Yeah, you plug it right back in here, right? This same value, since this is happening at the same temperature, we plug that into here. We already solved for Q, so we plug that in here. All you got to do is figure out delta RG, right? So why don't you do that and then answer this question. The question asks, indicate the direction. There's no responses here. Indicate the direction. But it says indicate the direction. All right, I messed up this one, so we will skip this question. I clearly messed it up when I wrote it. And I messed it up by closing it. Yeah, I'm going to stop that one, because I think I messed it up. Because I'm getting all sorts of answers. Okay, let's just do it together. Oh gosh. Okay, so to do this, we're just going to say delta RG equals negative 18377 plus RT natural log of 0.05. Which gives us what number? Negative 42 kilojoules-ish?
No, negative
42,000.
Okay, so negative 42 kilojoules.
What's the R value?
Right? R value is 8.3144 joules per mole, right? So that said, does this go forward or not?
Yes.
Yeah, it means that we're not done yet. From these initial starting conditions, we now know that the reaction must keep going forward, so we're going to produce a higher partial pressure of SO3, and these two are going to get consumed, so they're going to go down. Okay, any questions on this? This straightforward? Straightforward? I think there's a lot of thermo leading up to it, but now it's not so bad to use, right? We got 10 minutes left, let's do one more. Okay, true or false? If I calculate delta G naught, delta RG naught, excuse me. Actually, this might be the next question. Let's see if this one's broken too. Oh, there it is. So everybody, get your free points and type forward A. You were here in class. You got a free point. Type A. Another 20 seconds to get your points in. Okay, everybody good? No? Okay. We're not good. Type A in your machine. It was negative. We had written this. We produced more product. Forward, it's going to generate. If it's negative, that means it changes from products to reactants. From reactants to products, lowers the energy, so phase. And the product will get so A. Okay, we good? No? Oh, send me an email, Antonio. I can get your point. Okay, good? All right, we're good. And good. I would lose. Okay, that's the last one for today. So let's do this one right here. If I can calculate delta RG at room temperature, and then I want to determine whether or not a reaction occurs at 900 K, I just solve for delta. I'm sorry, I put these R's in the wrong spot when I made this slide. delta Rg equals delta Rg naught plus RT natural log Q. I just solve for this equation by substituting in T equals 900K and using the same delta Rg naught from 298 right here. And I see whether or not delta Rg is negative or positive. I'm gonna roll. What do you think? True or false? We're not doing a clicker, so just like raise of hands true. Jake. Raise of hands false. It's false. Why is it false? Is it Shannon? How come it's false?
You can have a different Q value if you have different concentrations or pressure.
Okay, so Q, okay, this is assuming that we could calculate Q at 900K.
Okay.
Even if we could calculate 900Q at 900K, what would be wrong about this approach? This is temperature dependent, right? That thing depends on temperature. As you're going to learn on homework question, I think 3, the cobalt one, the cobalt oxide one, you're going to learn that that depends on temperature. And to solve that question correctly, you have to keep into account its temperature dependence, okay? So it's false. And the reason why is because delta Rg naught, comma 298K does not equal delta Rg naught, comma 900K. Right? They're temperature dependent. Okay, next question in the 7 minutes we have left. Let's consider this reaction. If you've got an electrochemical reaction between silver or copper, Josh.
Is 298 going to be the room temperature value?
Yeah, in this class, 298 will be our standard value. If you use 300, it's fine. You'll get basically the same thing. 298 is the room temperature value, okay? So this electrochemical reaction, you got silver and copper, okay? And I've given you the reduction potentials. This is exactly what I would do on like an exam. I might give you these things. I'll probably throw in a few extra red herring ones that don't matter at all, right? And I say copper metal in 2 molar solution of copper 2 plus ions, and silver metal is in a 0.5 molar solution of silver plus ions. What is the observed delta V at room temperature? What's the approach here? What's the very first thing we do? We have to flip the sign of which one? The less positive one, the more negative one, so copper gets flipped. Which allows us to then say that delta V naught is going to be equal to 0.8 plus negative 0.34 volts. Right? So it's going to be some number. Okay? What's the next step once we know that number? We then let's write out our equation that we're going to use. Right? We'll say that delta V, not delta V naught, but this equals delta V naught minus RT over NF natural log of Q. Okay? What is N in this case? N is the number of electrons, and it's got to be what number? It's got to be 2, right? Because we have 1 electron up here, but we have 2. By the time we flip the copper and add those 2 equations together, electrons have to cancel out. So that means that this one needs to be multiplied by 2. Right? You got to multiply that one by 2. Otherwise, you won't have the right number of electrons. Okay? So, say this is the number from before, whatever that was. Right? It's going to be minus RT times that 298K. Let's just write it all out. Minus 8.3144 joules per mole K times 298K. This whole thing is going to be over 2 times 96,500 coulombs per mole. A joule over a coulomb is just a volt, so we're okay. That's going to give us the answer in volts. Multiplied by natural log of what will this be? What's Q?
Concentration.
It's going to be products over reactants. Our copper got switched. We've got copper 2 plus ions plus 2 electrons, right? So our products are what? What are the 2 products of this reaction? Silver metal, we ignore it, it's a metal, it's a solid, and copper, the oxidized species, which in this case is copper, right? So we're going to say the concentration of copper 2 plus, does it need an exponent? Why does it not need an exponent? Because the coefficient's 1 in the balanced equation, okay? Down here, what are we going to have? Yeah, it's going to be the concentration of silver ions. Does it need an exponent? It does, because we had to multiply this whole thing by 2 to get 2 silver ions. So that's got to have a 2 there. We don't need to worry about copper metal because copper metal is a solid, its activity is 1. Okay? So in this case, what is the observed delta V? We just plug all these in, we're going to get a value. And generally speaking, it'll be pretty close to the value here because this doesn't change it too much normally. Okay? Questions on how to do this? Yeah. F is just a constant. It's a constant just like the gas constant. It's called Faraday's constant. It says that there's 96,500 coulombs per mole of substance, well, of electrons actually. That's just, if you had a mole of electrons, what would be the charge of them? That would be the charge, 96,500. And then, remind me your name? Carl. Oh, Carl. Yeah. That would be, this is 2, and that's 0.5. Well, 0.5 squared. Okay, enjoy your weekend. Enjoy your long weekend. See you on Wednesday.
Yeah, so I remember on the first question, when you need to calculate the potential.
Okay.
I remember like in the product there is actually a chlorine ion in addition to the gold ion.
Yeah.
Do we need to take into account of that?
Here's what you this will only be minus 1. So this top light is minus 1, and then this side is going to rest. So with the reaction, you add your electrons, I forget the number, right? You're going to end up with chlorine that's still minus 1. So this chlorine at this point hasn't changed its oxidation state. So if you wanted to rewrite this, you would just ditch this and write it as 3+. Since chlorine doesn't change its oxidation state or its valence state, then it's not involved in the redox reaction. It's kind of a red herring. Make sense? Yeah, thank you. Question?
My phone wouldn't connect to the app for the first question.
Just send me an email.
Okay, well, thank you.
If you just email me, if that ever happens, just send an email. I'll give you the points for the day.
Just send the email right away? Or just...
After class or whatever.
Okay,
it's fine.
cool. Thank you.
So I'm just curious, you said we have like a couple sections we're supposed to read from chapter 16 and
16.1, 16.2, and 16.2.
Is there any, I don't want to like give you more to do, but is there any way you could like list that for each chapter that we're going to do?
Everything else we read everything.
Oh,
This is the only chapter that.
Okay, cool. I was just curious.
Just real quick. Yeah, good question. How do we know these are like if the voltage is positive or negative?
Like whether it gets flipped or not?
No, so like this one, this equation, voltage
that's given as positive.
Okay.
This one was given as negative and then we flipped it.
I know how it flips, it just is already given there on a table.
Yeah, the table, like if we scroll back up, take a look at this. The table will say,
It's in the table. It's like, how does it know?
yeah, no. It'll say like right here, see like they start out positive, they go negative. So it'll state it. Yeah.
Sorry, quick question. So when we compared change in GR 900 and then 690.
Yeah.
Not any class, could you also say that like that change in G is calculated as minus change in H would S.
One more time. I lost me a little bit.
So the change in G
is
calculated from H minus S change.
Okay, that's delta G. Yeah, that's it. Yeah. So delta G are not right. So the standard formation equals right. Minus T times delta.
And that's so that could be.
These are the not.
I just wanted to make sure that like.
Yeah, this is specifically for it's this not value.
Yeah.
Bingo.
Thank you.
No problem.
Not always great. Yeah, that's better. Thanks.
Yeah, no problem. Anything good? Yeah. You guys got plans for the weekend? Do anything fun?
No.
No fun plans, just sleeping.
I don't know.
That's all my wife wants. Like I always plan these things and she's like, just stay home. You just watch the kids and let me just sleep. So I will spend Saturday sleeping and Monday doing an adventure.
Is there a box to put in here?
Yeah, did you give
Homework? So we have the old box with the blue folders. That's not the wide one. It's got the old nasty yellow tabs, which are all folded over.
I have new ones that like.
You had that green ones with like they were really nice, but it's 15-inch wide folders, and we can't find any box that
you have tabs.
Unless you, and we can't 3D print one because it's larger than we can do. So, and I can't find one on Amazon.
Yeah.
So I'm at a loss. So until somebody wants to woodwork me one.
I have new sticky tabs.
You just want to use that then? And we're only gonna keep them for 1 week. And as soon as 1 week's over, if they don't get picked up, we throw them in the mega box in Josh's office, and the students pick them up there. We're not gonna deal with accumulated homework.
Yeah,
Ain't nobody got
they're
time
like
for
a
that.
paper clip that sticks on.
So it
instead
won't
of
get bent over.
sticking, and then they have a little tab that sticks out. So
That's way
they
better.
should be pretty good because then they won't like peel off.
He's already gonna be up a creek, I think. And if that's indicative of what he's gonna be doing, I might chat with him and tell him stop